Hello, everyone. My name is Malia Ram, and today I'm going to be talking to you about my research this summer where we were searching for unassociated Fermi objects with the highest energy gamma rays in the galaxy. So first, this is just an outline of what I'm going to be talking about today. So first, I'm going to introduce you a little bit about cosmic and gamma ray astronomy, and then I'm going to talk to you about the observatories and the catalogs of data that we worked with this summer. And then I'm going to explain our method, our results, and then conclude the presentation. So first off, what are cosmic rays? Well, these are charged atomic nuclei that are bombarding us constantly from all directions. And these are usually produced in the most violent events in the universe, such as supernova explosions and the supermassive black holes at the center of the most active galaxies. And this graph on the left shows the flux of cosmic rays as a function of their energy. Now, what I want you to take away from this very busy graph is that there have been observations of cosmic rays with energies above 10 to the 20th electron volts. Now, this is an unbelievably large amount of energy. And to put it into context, the now famous Large Hadron Collider in Europe can accelerate protons up to energies of 10 to the 14th electron volts. So the largest, most complex particle accelerator we can build is short by a factor of 1,000,000 of astrophysical objects can do. Now, the trillion-dollar question is, what are these accelerators? Well, using cosmic rays, we cannot find where these objects are. So this picture on the right shows the trajectories of different particles emitted from an astrophysical object approaching the Earth. And the red line is a cosmic rays trajectory. Now, because cosmic rays are charged particles, their trajectories are bent by magnetic fields from other galaxies, so that by the time they reach us, we don't know their origin. So this is the reason why, to find the accelerators, we instead study gamma rays or particles of light. These are called photons. So photons have no electric charge and they come directly to us from their sources. And this is why we've been doing astronomy for thousands of years. And this blue line shows the straight line trajectory of a gamma ray. So we observe photons across the entire electromagnetic spectrum that I'm showing you right here. And the horizontal scale indicates the energy of the photons increasing to the right. And in this study, we looked at photons with the highest energies, which are X-rays and gamma rays. So how do we study these gamma rays and determine their sources? Well, we use detectors. And one of them is the Fermi satellite, which is a satellite in space that holds an imaging gamma ray telescope. Now, the most important part to remember is that the Large Area Telescope on this observatory detects directly gamma rays in the lower energy range from 20 MeV to 300 GeV, so from 10 to the 6th to 10 to the 11th electron volts. So this is a sky map of Fermi's field of view, and Fermi observes the entire gamma ray sky, and those little dots at the top and bottom are many galaxies, and that bright band running along the middle is made up of gamma ray sources along the galactic plane. And also these sources are plotted in galactic coordinates. So as I mentioned before, the Fermilab studies gamma rays in the energy range from 10 to the 6th to 10 to the 11th electron volts. And this in turn means that cosmic ray sources are studied up to 10 to the 12th to 10 to the 13th electron volts. But it has no sensitivity to higher energies because of its limited size. So looking again at the graph of cosmic ray fluxes, a satellite of about 1 square meter will only detect a handful of cosmic rays per year. So then to reach higher energies, we would need a much larger detection area, which is impossible to put up in space. So therefore, we would need to use another technique called indirect detection, where we use a ground-based detector big enough to observe high energy gamma rays through their induced air showers. So cosmic rays and gamma rays are constantly entering the Earth's atmosphere from space. And after one of these high energy particles enters the atmosphere, it will interact with surrounding air molecules, creating a secondary particle shower, which you can see here. So we observe the original high energy particle by detecting the secondary particles in these extensive air showers. So the HAWC Observatory is one of these ground-based detectors that studies very high energy gamma rays to the detection of their induced showers. So HAWC is made up of 300 water Cherenkov detectors, and it observes about up to 2/3 of the gamma ray sky. And this detector also detects gamma rays in the so-called very high energy range of 500 GeV to 100 TeV. So from 10 to the 11th to 10 to the 14th electron volts. So this picture here is HAWC's field of view. And this time, this sky map is in equatorial coordinates, unlike Fermi's, which was in galactic coordinates. And that bright band of gamma ray sources is, again, the galactic plane. And HAWC is located in Mexico at 19 degrees north, which corresponds to a horizontal line in the middle of this map. So this picture here on the left is a simulation of a cosmic ray-induced air shower. And at the top, the primary particle enters the atmosphere and collides with surrounding air molecules to initiate the particle cascade. And on the right shows how the HAWC array detects one air shower as it reaches the ground. The next thing I want to talk about are the catalogs from the HAWC and Fermilab observatories. And these are the catalogs that we worked with this summer. So the 3 HAWC catalog consists of HAWC data from 65 gamma ray candidate sources in the tera-electron volt energy range, that is 10 to the 12th electron volts, with 20 of them being unassociated sources. And this sky map here, again, is the HAWC's field of view, but in galactic coordinates. And we also looked at the 4FGL catalog, which is Fermi's 4th catalog. And this has data from 5,064 sources in the GeV range, or 10 to the 9th electron volts, with 1,410 of them being unassociated. So it's natural to observe so many more of these sources because you have to recall how the fluxes go up with a power law for lower energies. So what do I mean by unassociated sources? Well, first, this picture here is a significance map of the 3 HAWC catalog along one given section of the galactic plane. And this color scale at the bottom indicates where the most significant excesses are. And the labels at the bottom of the graph are from the 3 HAWC catalog, and the ones at the top are from a catalog of known gamma ray sources. So the 3 HAWC excesses with known sources within a distance of less than 1 degree are deemed associated sources. So for example, 3 HAWC J1922 plus 140. But however, there are significant excesses that don't have any known sources nearby, like 3 HAWC J1940 plus 237, that doesn't have one. And these are called unassociated sources. So this is the same case for the unassociated candidate sources in the 4FGL catalog observed with Fermilab. So again, it's important to emphasize that these sources have never been observed before. These significant excesses have been observed only with either HAWC or Fermi. So they could be real gamma ray sources, or they could just be fluctuations from the background. So the goal for our project was to find spatial correlations between the data of the 3 HAWC catalog and unassociated sources from the 4FGL catalog to hopefully identify new gamma ray sources. And the importance of our research is that if we can determine the source of these higher energy gamma rays, we can then determine the objects behind the acceleration of the high energy cosmic rays that reach us on Earth. This is part of our method. So first we cross-correlated the 2 catalogs and defined a spatial association criteria for unassociated Fermi sources within a distance of less than a degree of a 3 HAWC excess. We also plotted these candidate sources with their 3 HAWC counterparts on significance maps. So for example, in our calculations, we discovered that the source 3 HAWC J1847 minus 017 has one unassociated source detected by Fermi that was located 0.15 degrees away from it. And this is the significance map for this 3 HAWC source. So in our results, we found 14 3 HAWC excesses with unassociated Fermi sources nearby. And I showed you 2 examples in this slide, each with the closest candidate source. And the source on the left is observed by HAWC as a point source, while the one on the right is observed as an extended source, which basically means that the observed emission extends much further than the point source of this telescope. So there are 3 extended regions out of the 14 candidate coincidences that we looked at. So to further narrow down our search, we decided to investigate these sources at an even lower energy range. So to do this, we looked for previous observations made with the SWIFT satellite with the help of a graduate student who's currently working here in the astronomy department. And SWIFT is another satellite designed to observe X-rays. So we looked for data from the Burst Alert telescope on the satellite, which operates in the energy range between 15 and 150 kilo electron volts. And of the 14 selected sources, only 3 of them had significant X-ray excesses near them. So in this picture on the right, these bright spots that you see here are significant X-ray excesses that we see from SWIFT-BAT. And of these 3, only 3 HAWC J1837-066 had the X-ray excess within the angular uncertainty region of the associated gamma ray source. So this red circle here is 1 degree around the 3 HAWC source, and we can see the possible association between the 3 experiments. This brighter spot is the X-ray source, and the green circle is the Fermi unassociated source, and also the red circle is the field of view of HAWC. So we felt that this was the most significant spatial correlation that we proposed we should study even further. So what do we find in our results? Well, first, we found at least 1 significant association from 3 different instruments across 10 orders of magnitude in energy. And this is unbelievable because we were able to find coincidences from 3 independent instruments covering an energy range from 1 up to 10 billions. So this is very likely a new gamma ray source and not just a random fluctuation of the background. So to pursue the study even further, we would like to study the energy spectrum measured by the 3 experiments and use this to actually pinpoint the actual astrophysical object behind the gamma ray emission. And to do this, we would need to prepare a target opportunity proposal, or TOO proposal, to request observation time with the SWIFT XRT, or X-ray telescope, which is another instrument on SWIFT that operates at an even lower energy range at X-ray energies from 0.2 to 10 kilo electron volts. And that concludes my presentation. So thank you so much for your attention, and I hope you had fun learning about my research just as much as I did doing it. Thank you.